So this tutorial sessions focus on the open sets and closed sets, right? Uh, so we have discussed a lot of theory mm, on open sets and closed sets, right? But here the tutorial focus on how we are going to determine how to determine the given set as either open or closed or neither open or closed, etc. Right? So, uh, in this one, there are five problems, but I will focus. I will try how many questions I am going to complete, right? So, before going to solving these problems, we have to check basic theory what we discussed, right? So, what is the open set? Open set, suppose X is a metric space and A is the subset of vector X. So now I am going to say the set A is an open if every point in A is an interior point. So what does that mean? Suppose X belongs to A and said to be an interior point if there exists R greater than 0 such that the open bar with center X and radius R should be a subset of A. So that is called an interior point. So if you want to say A is an open, if every point is an interior point, right? Um, so similarly, we have proved some properties in class. What is that one? Mm, A is open if and only if, right? A is equals to interior of A. What is the interior of A? That is set of all interior points of A, right? So that is our notation, interior of A. And also we are represent a circle like this one. So A is open if and only if A is equals to interior of A. So when we are going to prove, because see here, interior of, by definition, interior of A is always subset of A, right? So if you want to prove that A is open, if you have to verify A should be a subset of interior of A. That is, take an arbitrary element in XA implies X belongs to interior of A. That is one of the procedure to show that given set is an open set, right? Or another approach. Suppose you have a lot of open sets. Then if you show that, for example, Gi be the collection of open sets, then their union Gi is equals to G is also open, right? And similarly, finite intersection of open sets is again an open, right? And also there is one way, if you show that the complement of A is closed, then A is, so these are all possibilities. So majority, we have to use this information. And what is the, how do we show that the given set is a closed, right? Same way, uh, of course, this is to show that interior of for showing the open, and also there are some techniques we can use that one. So here x belongs to A implies x belongs to interior of A, right? And also the contrapositive of this statement, right? So you can take, there is a one point x belongs to A and which is not an interior point of A. So then automatically interior of A is not equals to A. Hence A is not open. This is also possible, right? And again, you can take a specific point x belongs to A such that for all r greater than 0, the open ball P of x comma r contains point y which is not a member of A. Of course, that point is depending on the value of the radius r. So it follows that x is not an interior point of A, and hence A is not open. And similarly, if you are showing that the complement of A is not closed, then A is not open. So similarly, in the case of the closed set, you can prove that A complement is open. If A complement is open, then A is closed, right? So if you want to show that A is a closed, just you have to show that A complement is open. And we know that A prime is equals to set of or limit points of A. What is the limit point? This is a metric space. This is a A. So you can say X belongs to capital X. If you want to say X is a limit point of A, then for each uh, r greater than 0, right? The open ball B of x comma r, right? Different from X, intersection A is non-empty, right? Uh, if you show that one, then okay. Uh, so let me go back. So limit point. So limit point mean this is a limit point of A, mean every radius R contains at least one point of A other than X. That is called a limit point. So in the notation, we can see this is the way to represent the definition as a limit point, right? So in this one is non-empty mean automatically uh, uh, there is a point y which is a common in this set and A. And also we can verify the finite union of closed sets is again a closed, and any arbitrary intersection of closed sets, right? Intersection of Fi is equals to F, say, is closed, where each Fi is a closed sets. So this is the way to show the given set is closed set. And similarly, how do we show that the given set A is not closed? Generally, we discussed one theorem. So A is closed, right? By definition, every limit point of A is a point of A. That is A dash is a subset of A. Suppose if A is not closed, then A dash is not subset of A. And also from this definition, right? Sometimes X is a limit point of A, but X does not belongs to A. In such a case, we can say that one is that set is not closed. And similarly, the A complement is not open, then A is not closed. So all these are the possibilities to show that the given set A is either closed or not closed. So please refer the material what I uploaded in my learning. It is easy to understand, right? Okay, right. So now I need to focus on the example 2 and example 5, right? So the remaining almost all we have discussed, and you can easily understanding what is the uh, way to prove those sets are open or closed or not open or not closed, right? So now I am focusing on question number 2. What is that one? X is 0 comma infinity, right? This is my given set, and D is a function from x cross x to R by D of x comma y is equals to modulus of ln x minus ln y, right? That is natural logarithms ln x ln y for all x comma y belongs to 0 comma infinity. That is our x, right? Of course, this is a metric space. I didn't prove that that is a metric space axioms, right? What is my question here? A. Determine open bar right. B. The center 1 radius ln2 right, and hence R on the closed bar B of 1 comma ln2 right. So first we will show this. Of course, there are two more parts. After this one, we will see how do we prove the circuit, right? Okay, right. So what is the open bar here? B of 1 comma ln2, right? That is set of y belongs to x. You know that what is the x 0 comma infinity, such that the distance of 1 comma 1 comma y is less than ln2. But what is your metric? That is set of y belongs to x such that modulus of, right? That is ln of 1 minus ln of y is less than ln2. So you can expand the modulus, that is set of all y belongs to x such that minus ln2, right? So ln1 minus lny less than ln2. That is set of all y belongs to capital X such that, right? ln1 is a 0. Then I can write this is minus ln2 is less than. Of course, you can also change here lny minus lny, right? For sake modulus, no problem. That is minus ln2 is less than lny is less than, right? So what is this one? This one I can write y belongs to capital X minus ln of 2 to the power of minus 1 is less than y less than ln2. That implies set of all y belongs to capital X such that ln of 1 over 2 less than lny is less than ln2. So that implies I can write, you can remove the ln set of all y belongs to x such that 1 by 2 is less than y is less than 2. So simply that is, this is an interval 1 by 2 comma 2. So this is an open bar. Similarly, you can verify the closure, just it is a less than or equal P of 1 comma ln2, which is equals to 1 by 2 comma. So that is the first part. What is the second part? In this second part, what we are going to show, I need to show that the set Q intersection 0 comma is neither open nor closed. in 0 comma infinity with metric p. What is the metric? With metric p. It is p of x comma y is equals to modulus of ln x minus ln, right? So with respect to this metric, this set is neither open nor closed, right? Hmm. So now what we are going to prove first of all, we have to show that, right? Two intersection, that is set of rational numbers, the section 0 comma 1 is not open in the interval 0 comma infinity, right? With this metric D, right? So for this one, what I am going to show that, take one point. So what I told, if let us say this is A. So A is not open mean, what I am going to say, I want to take one point, X belongs to A, right? Implies X does not belongs to interior of A. That is, X is not interior point, an interior point of A, right? So what I am going to do, for any R greater than 0, right? I am going to consider the open bar. What is the open bar? V of with the center 1 by 2 and radius R. So that is equals to set of R. Y belongs to capital X. What is your X? That is 0 comma infinity. Such that the distance of 1 by 2 comma Y is less than R by definition. So that is equals to set of all Y belongs to capital X such that what is the T of 1 by 2? So that is modulus of ln 1 by 2 minus ln Y is less than R. So I can write that is set of all Y belongs to X such that for sake of convenience, uh, I need to change the Y and 1 by 2 positions, right? That is ln of Y minus ln of 1 by 2 is less than R. So what is that meaning? That is set of all Y belongs to X such that minus R is less than ln Y. Ln of Y minus ln of 1 by 2 is less than R. So that is equals to, you can take the Y belongs to capital X such that I am adding ln 1 by 2 on both sides. That is ln 1 by 2 minus r is less than ln y. So minus ln 1 by 2 plus ln 1 by 2 cancel is less than ln 1 by 2 plus r. So I can take that one as set of R y belongs to capital X such that. So now I am going to do the e power, right? So if I am taking the exponential, what will happen? That is e to the power of ln 1 by 2 minus r is less than y, because e to the power of ln y is equal to y is less than e to the power of ln of 1 by 2 plus r. So that is simply what is this one? Set of R y belongs to capital X such that y belongs to an interval e to the power of ln 1 by 2 minus r, right? Comma, comma, e to the power of ln 1 by 2 plus r. So what is this set? Set is nothing but the open interval 1 by 2 times e to the power of minus r, comma, uh, 1 by 2 times e to the power of is interval, right? Now, what I am going to discuss it, we know that the function natural logarithm ln is an increasing function, right? So we know that what is the dense property? Dense property, rationals in R, real life. There exists a W belongs to Q complement. What is the Q complement? That is irrational numbers, right? Such that 1 by 2 to the 1 by 2 times e to the power of minus half is less than W is less than 1 by 2 times e to the power of half. So between two irrational numbers, there exists one. Sorry, between two real numbers, there exists one. What is this? Irrational numbers. Right? So what we concluded here, therefore, this W is an irrational number which belongs to the open 1 by 2 comma R. So in such a case, this is not a subset of Q, right? Once it is not a subset of Q, then it is not a subset of Q intersection 0 comma 1, right? So what is that meaning? 1 by 2, not an interior point, right? Is not an interior point of the set Q intersection 0 comma. So therefore Q intersection 0 comma 1 is not an open set. So I took an element, right? I construct a open bar. In that open bar is not a subset of the given set, so that point is not an interior point. So that is 1 by 2 does not belongs to interior of A. Our A is equals to interior of 2 intersection, right? With respect to that is our metric T, right? So similarly, we can also show that the set is not closed in 0, comma infinity with respect to the metric T of x comma y is equals to modulus of ln x minus modulus of ln y. Isn't it? Right. So what is our mechanism? So now with respect to this metric, now we are going to show that the set A is equals to Q intersection 0, comma 1 is not closed in the space X, that is 0, comma. So what is mechanism? So we took a one limit point, but that limit point is not a set in the set A. So that is that the set of limit points is not a subset of A. So A is closed if and only if A dash is subset of A. A dash is the set of all limit points of A, right? Isn't it? Let us, okay, see. So for this one, what we are going to show that, let us take 1 belongs to Q intersection 0, comma 1. Of course, 1 is not a member of this one, but 1 is a limit point, right? 1 is a limit point of this set A, isn't it? Okay. What is this mechanism? We'll see. Take any real number or greater than 0 and consider an open bar B of x comma r. What is this B of x comma r? Same. In place of x, you can take B of 1 comma r. The procedure same as it is nothing but e to the power of minus r comma e to the power of r. So before we took 1 by 2, so that's why here 1 by 2 times e to the power of minus r and e to 1 by 2 times e to the power of 4. But here x is equals to 1. This is your uh, open bar with center 1 and radius r. So you can see the material proof is explained. Of course, it is a similar what I explained in before, right? So now, what is that one? 0 is less than e to the power of minus r, which is less than 1. which is less than e to the power of r, where r is greater than 0. So what is the density of the rational numbers? Density or dense property of rational numbers. Dense property of rationals in R, right? There exists a Q belongs to, small q belongs to capital Q, such that 0 is less than e to the power of minus r is less than q is less than 1 is less than e to the power of r. So that implies where q belongs to p of 1 comma r different from the singleton set 1 and q belongs to q intersection 0, right? So what is that meaning? This implies that q is a small q is a member of p of 1 comma r different from 1 intersection q intersection 0 comma 1 is non-empty, right? So if it is a non-empty, what is that meaning? That q is a limit point of q intersection 0 comma 1, right? So q is a limit point of this one, but that is not a member of uh, uh, in the set q of 0 comma 1. So that's why that implies q intersection 0 comma 1 is not closed. So with respect to the metric T, isn't it? So one is what I proved, we construct open bar, center 1, radius r, and different from 1, intersection q comma 0, 1 contains 1 point. So not q, this is a 1. 1 is a limit point of q intersection 1, but 1 is not a member of q intersection 0 comma 1. 1 is a limit point, but 1 is not a member of this one because here is a open interval 0 comma 1. So that's why the set is not closed. Isn't it? But however, if you are consider the discrete metric on q intersection 0 comma 1, then that is open as well as closed, right? What is the other part? Last part C, right? Q intersection show that Q intersection 0 comma 1 is both open, right, and closed whenever x that is equals to 0 comma infinity with respect to discrete method. So proof is simple. We verified lot of problems in class, but it is available detailed proof in your material. We check that, right? So next, what is the remaining all problems are similar. So we have to verify, and some of the problems also verified in class, right? So now I am going to focus on the fifth problem. What is the fifth problem? That is some interesting to discuss, right? So we know that C of 0, comma 1, let us say that is a x. We know that that is a set of all continuous functions defined on x on 0, comma 1, right? So we know that this x is a metric space with respect to d infinity. What is the d infinity of f comma z? That is equals to supremum of modulus of f of x minus g of x, where x belongs to 0, comma 1. We know that this is a metric, and hence that is a metric space, right? So supremum metric d infinity, this is a metric space. So, okay, that is not my question, right? Suppose A is equals to, right? Set of all f belongs to x such that f of x, f of x is strictly greater than 0 for all x belongs to 0, comma. So this is clearly a subset of x, because in capital X, there are continuous function, either positive continuous, negative continuous, or equal to 0, constant, all types of functions are there. But what is my subset? It consists of all non-negative functions which are defined on 0, comma 1 and continuous. That is. Now, what is my target? My target is to show this A is open but not closed, right? It open but not closed itself, right? So, number one is open, number two is not closed. Quotes. Isn't it? Okay. Proof is very simple and interesting. Okay. So, what is our mechanism? How do we show that A is open? Right? That is what we are going to show, that A is open. So, that is the every interior point, every interior point of A belongs to A. That is interior of A is a subset of A. Right? Okay. Right. We need to see one by one. Let us take, let F belongs to A. Of course, A is a subset of C of 0, comma 1. That is our X. Right. So, what happened according to the definition of F of X is greater than 0. But what happened? F here, continuous function. Okay. F is continuous. Where it is continuous? On closed interval 0, comma 1. This is compact. Once the continuous function defined on compact, then F has, right, uh, attains maximum and minimum, right? F attains maximum and minimum. That is simply F is bounded function. So, let us say uh, there exists, right, by extreme value theorem, by extreme value theorem, there exists small m greater than 0, such that F of X is greater than or equals to n, and m is greater than 0. Right? So, F of X is greater than 0. Right? So, uh, mm, right? F of X is greater than or equals to m. Of course, m is greater than, so F of X is greater than 0. Right? Now, I am going to consider open bar. Right? Consider open bar. Right? Center F function. Radius is m. That is equals to, by definition, G belongs to C of 0, comma 1, such that T infinity of F, comma G is less than m. Right? So that is less than m. That is equals to set of all G belongs to C of 0, comma 1, such that, what is that one? The supremum of modulus of F of X minus G of X, where X belongs to, where it is 0, comma 1, less than m. So supremum value is less than m mean, that is G belongs to C of 0, comma 1, such that the modulus, each term, each function F of X minus G of X is less than m, right? Okay, no? So that is, I can say G belongs to C of 0, 1 for convenience. I am writing G of X minus F of X is less than m. Then I am going to expand what is my modulus value. Minus m is less than or equals to G of X minus F of X is less than m. So what is this one? This is G belongs to C of 0 comma 1 such that adding f of x on both sides, f of x minus m is less than or equals to g of x. Sorry, it is strictly less than, and g of x is less than f of x plus m, right? For all x belongs to 0 comma 1, right? For all x belongs to, then so now this is my open bar. So open bar means all your g of x values lies in between f of x minus m and f of x plus m. Okay. What I am going to take? I am going to take one function h in b of f comma m, right? Let h belongs to b of f comma m. Then where h is, that h is f of x minus m is less than h of x is less than or equals to less than f of x plus m. What I am going to take? I am going to take this left hand inequality, right? Without loss of generality, no problem. I'm going to take the left side inequality, right? So this is for all x belongs to 0 comma 1. So now, since f of x minus m is less than h of x, implies h of x is greater than f of x minus m, right? But what is the f of x? F of x is greater than m, so that is m minus m, that is equals to 0. So your h is greater than 0. If h is greater than 0, what is that meaning? That implies h belongs to a, right? So what happened? This is h belongs to a. So what we did? There exists small m greater than 0 such that open ball B of f comma m is a subset of A. That implies f is an interior point of A. That implies f belongs to interior of A. Where did you collect? First, you took f belongs to A and you prove that f belongs to interior of A. So every point of A is an interior point. Every point of A is an interior point mean by definition A is open, right? So that is proved. So what is the next one? This set is not closed, right? So if this set is not closed, I am going to show one function in A, right? Of course, zero function I am going to take. So now we will show that the set is not closed, right? What is that meaning? For this, right? We will show that the zero function, of course, is not a member of A because all functions should be a greater than 0. So 0 function is not a member of A, right? But it is a limit point of A, right? That is 0 belongs to A prime, but 0 is not a member of A. So that is every limit point of A is not a point of A. Automatically, by definition, it is by property, it is not a closed, right? Okay. So take any real small or greater than 0 and consider uh, the constant function g of x is equals to 1 by 2 for all x belongs to 0 comma 1. Let us say r by 2, right? What I am going to show that? We will show z belongs to v of 0 comma r, which is different from 0 set, right? Intersection A. So what is that meaning? That is G is a limit point of, right? Okay. So what is the G? First you should note that G is a constant function. So that implies G is a continuous. And G of x is equals to r by 2, which is greater than 0. That implies G belongs to A, right? Okay. Mm, Not necessary. Of course, no problem. You can see. This 0 is a 0 function, not a number, right? So G is a, not G. This is 0 is a limit point, right? 0 is a limit point of A because the function G is a intersection of the open ball different from 0 and A, right? So not A. Okay. So what is the G belongs to? Hmm. Of course, C of 0 comma 1, no problem. The D infinity of 0 comma G is equals to supremum of 0 function minus G of x, where x belongs to 0 comma 1. That is equals to supremum of mod G of x, where x belongs to 0 comma 1. But we know that is equals to r by 2. R by 2 is less than r. So your Z is a member of G is a member of open ball 0 comma R. That is the set of G belongs to C of 0 comma 1 such that D infinity of 0 comma G is less than R. So G is not a zero function. It is a constant function which is R by 2. So, G is a member of P of 0 comma R different from 0, right? And G belongs to A, right? And G will to this one and G belongs to A because G of X is R by 2, R by 2 is greater than 0. So in such a case, G is a member. So therefore, the G is a member of P of 0 comma R slash 0 intersection A, right? So the element G contains of this one. So that implies 0 is a limit point of A. That implies 0 belongs to A dash, but 0 does not belongs to. Hence, if every limit point is a point of A, then that is a closed. So here 0 is a limit point, but 0 is not a member of A. Hence, A is not closed, right? So this is few examples. That is, A dash is not subset of. So these are the some of the examples in your tutorial sheet. So now closed session. We'll see. Okay, bye.